Okay, and now we're finally going to get to Jacob's question, which is construct a 2 by 2 matrix whose null space is its column space. And then it tells me this is possible. To which I say, yes, it is. Okay, so for one thing, the null space is usually where? Don't get this wrong, it's written right above this.
I'm going to take a wild guess and say in the domain.
Good, so the null space is in the domain. Where's the column space?
It's the range. In
Good, the column space
codomain
is the range. It lives in the codomain, right? And so if I have a 2 by 2 matrix, does this make sense that the null space in the domain could be the column space in the codomain? I think that's only going to make sense because this is R, right? A 2 by 2 matrix maps R2 to R2. If I had a 2 by 3 matrix, I wouldn't have a chance in hell of doing this because they're just different dimensional. Does that sort of follow?
Yeah.
So it's a little bit special that we can even try this. Now, how in the hell do you do it? Well, you do it the same way you do everything. Start with the identity matrix. I don't know why I like to start everything with the identity matrix, but it's either the identity matrix or 0. Uh-oh, Jacob left. Oh, I get to watch a recording. All right, so if I have the identity matrix and I apply this, what's the null space? What does the identity matrix map to 0?
When the vector is 0.
Good. So the null space of the identity is the 0 vector. And what's the column space of the identity matrix? Span of the columns, I think, gives you everything, right? Okay, so I need something with a bigger null space and a smaller column space, right? So I'm going to try dumping one of those two ones. Which one do you want to dump?
The second one.
Okay. So this one didn't work. Oops. Maybe try that in a slightly less aggressive color. That one didn't work. So I'm going to try this one. Notice that's the PX matrix again. Okay, so what's the null space of the PX matrix?
Zero Y.
Good. So it's the span of the vectors 0, 1, right? Anything with 0 in the X and a Y in the... what's the column space? What do you got for columns in that thing? Normally I'd be like, well, shit, dude, it's the span of the columns, right? So it's like the span of 1, 0 and 0, 0. What does having 0, 0 in a linear combination do?
Nothing.
Bupkis.
Upkiss. Pitch it. Doesn't do anything. You can do that with spans. So if you have a span of a set of vectors, anything that's linearly dependent in there, you can pitch until you run out. It'll still be the same set. right? Because it's it's the set of all the linear combinations. And so if you can make some things two different ways, there's no reason to have them. So you just chuck them. All right, now, are these the same?
No.
Crap. What are they different by?
The 0 and a 1 being in the wrong spot.
Yeah, I need something that like switches the 0 and the 1, right?
So that would just be the get rid of the 1 on the top and leave it on the bottom one.
Okay, so you want to do this one?
Yeah.
Okay, so let's try this one. So the null space, I'm going to call this matrix key y for no reason at all. So the null space here is going to be the span of, and I'm a little bit out of time. Normally I'd let you do this calculation, but it's the things that look like x and 0. And then the column space for this thing is
never mind.
Good. Yeah, so this has the same problem, right? Now they're just switched the other way.
So instead of a projection matrix, you could use an elimination matrix?
Cool, so close.
I was going to say we could do the opposite of the identity matrix. So instead of 1, 0, 0, 1, we could do 0, 1, 1, 0, and then leave out the bottom left.
Good. Yeah, you can leave out, so you can take the anti-identity matrix, the permute 1, 2 matrix. That's what this thing is. This is the P1, 2 matrix that permutes row 1 and row 2. And then combine it with one of the projection matrices. So that's just dump one of these. This one is my favorite one. This is the switch x and y and then project onto the x. So this matrix, which we'll call maybe A, I guess. So the null space of A is, let's see, if I take a vector xy, I get 0 in the first component, and then I get 0 in the second component only if x is 0. So my null space is the span of 0 and 1. And what's my column space?
Same thing.
Same deal. Cool. These are handy to know. This lower triangular matrix that this one very conveniently has the property that because the null space is the column space, if you do this matrix twice, you get nothing. Get the 0 vector. You guys see that? This whole property means that A squared is the 0 vector. Well, sorry, I said the 0 vector. It's a 0 matrix. Does that make sense? No, that doesn't make any damn sense. Matrices shouldn't do that. You shouldn't be able to do a matrix twice and get nothing. It's dumb. Crazy, stupid thing. Very confusing. This says that not only is there not a 0 friggin' product rule, there's not even a, like, you can take the square root of everything. What a mess. You guys with me on that?
Yeah.
Yeah, these are special. So this property, where you have A to a power is the 0 matrix. So A n by n to a power gives you the 0 matrix. This is so special it has a word. It's called nilpotent. We're going to talk about it later. I don't care if you know this for right now, but if you want to put that word in your head, it'll save you some time later. Any other questions? Okay.